Hey guys, welcome back. So let's go over this stuff that I asked you to take a look at. So our percent composition examples. So the first thing we had, oh, let me share my screen. That's why I can't see anything. Percent composition examples. So what is the percent composition of MgCl2? So MgCl2, my Mg percent. Let's do the Mg portion first. Now I've pulled up this table because I find it nearly impossible to read the numbers on the periodic table that you've been given. So I'm looking at the mass for Mg, which is 24.305. 24.305 grams per mole. There's 1 mole. So that's 24.305 grams. There's going to be some mass I'm going to put underneath. We need to look at our percent Cl. So what's our mass of Cl? I know that he's somewhere nearby. He's number 17. So 35.453 from that periodic table, not from Alex. So 35.453 grams per mole times 2 moles. And my calculator says 35.453 times 2 gives me 70.906. And that's, again, grams. So if I take that 70.906 plus the 24.305, that gives me a total of 95.211 grams. So 95.211. Multiply that by 100. Actually erasing it because I already got the 95.211 grams underneath. So I take my 24.305. I divide that by the 95.211. Multiply by 100. And that gives me 25.528%. And then I take the 70.906 and I divide that by the 95.211. Multiply that by 100. And that gives me 74.472%. And again, if I add those two together, it gives me 100% exactly. So cool. Must be right. Awesome. I love it. Next thing says, what's the percent composition of H2SO4? So here I'm going to want a percent for H. Do that first. And again, my hydrogen listing for the periodic table is 1.008 grams per mole times 2 moles, because there's 2 in the H2SO4. That's going to give me 1.008 times 2 is 2.016 grams. My percent for sulfur, sulfur, 32.066 grams per mole times 1 mole equals 32.066 grams. And then percent oxygen equals 15.999 grams per mole times 4 moles equals 15.999 times 4 gives me 63.996 grams. Take a mass for those. Take the 63.996 plus the 2.06 plus the 32.066. Total mass there is 98.078. Multiply that by 100. Two point oh one six at 98.078. 100 gives me 2.05. 1, 2, 3, 4, 0.566%. 32.066 divided by answer the 98.078 times 100 gives me 32.694%, and then 63.996 divided by that 98.078 times 100 give me 65.250%. Adding those together, I end up with 100%, so that makes sense to me. And those are percent compositions for H2SO4. Right? Cool, H2SO4. Now I have the empirical formulas for two things. I'm going to go ahead and add another page so I can deal with that. And if I scroll back, I see empirical formula for a molecule that's 40% carbon, 0.00% C, 6.67% H, and 53.33% O. My process here is to assume that's out of 100 grams. So that means I would have 40.00 grams of carbon. We'll convert that to moles by dividing by the molecular weight of carbon. Again, carbon is here, so he's 12.011 grams. 12.011 grams for 1 mole of carbon. Gives me 3.330 moles of carbon. And take 6.67 grams of hydrogen. I divide that by the molecular weight is 1.008 grams hydrogen per mole of hydrogen. And it gives me 6.617 moles of hydrogen. And then I have my 53.33 grams of oxygen divided by the molecular weight, which is 15.919 grams of oxygen in the mole of oxygen. Which gives me 3.333 moles of oxygen. Now again, the way that I deal with this is to write carbon 3.330, hydrogen 6.617, And then oxygen, 3.333. And what I'm looking for is that whole number ratio. So I'm going to divide by the 3.33. And what I end up with is C1 H 1.987 and then O 1.001. So I can round this to 1. I can round this to 1. So I end up with CH 1.987. And that's close enough to 2. So CH2. Oh. Okay. So to whole number rounding, we can call that CH2O. Okay. That's how I would deal with that. Now again, this is close enough to 2 to make that work. If it was said 1.5, that wouldn't be close enough. This is close enough to 1 to make that work. Now, what's the empirical formula for a molecule that has 31.42% sulfur? 31.42% sulfur. 31.35% oxygen. And 37.23%. Again, we're going to assume that we have masses out of 100. So 31.42 grams of sulfur, 31.35 grams of oxygen, and 37.23 grams of fluorine. We convert that to moles by dividing by the molecular weight. 31.42 grams of sulfur divided by the molecular weight of sulfur, which again, 32.066. And 1.42 divided by 32.066 gives me 0.9795 moles of sulfur. 31.35 grams of oxygen divided by the molecular weight of oxygen, which is 15.999 grams of oxygen per mole of oxygen. 31.359 divided by 15.999. 1.960. 0 mole of oxygen. And then we're assuming we have 37.23 grams. 37.23 grams of fluorine. Fluorine again is 18.998 grams. (37.23) divided by 18.8 is 1.9. That moles of F. So I'm going to write that down just the way I've got it. So S 0.97985. O 1.9600. And F 1.9597. I'm going to divide everything by the smallest number. 0.97985. 97985. and 0.97985. And with an S, O2, and F, two. SO2F2. So the numbers I got out when I did this became O2.0004 and F 1.999. So, which again, I felt comfortable rounding to 2 and 2. Cool with that. So it's a little work. It is a little work, and it's kind of exhausting, but that's what we do with those. Questions, comments, problems on any of that? Hopefully not. Here is another example of determining an empirical formula by experiment. So we have 0.331 grams for iron. It's placed in a crucible covered with powdered sulfur. The crucible is heated until all of the excess sulfur is driven off after the iron reacts with the sulfur. Product weighs 0.522 grams. What's the empirical formula of the iron sulfide complex? Well, the mass of the sulfur is the 0.552 grams of the product minus the 0.331 grams of iron. And that gives us a 0.191 grams of sulfur that were incorporated into that compound. Okay, so that 0.191 grams of sulfur we convert to moles. We divide by the molecular weight and get 0.00596 moles of sulfur. We then convert the 0.331 grams of iron by dividing by its molecular weight to get 0.00592 moles of Fe. We then write, just like we always do, Fe 0.00592, S 0.00596. I divide both of those by the smallest number, and that reduces to FeS. Cool with that. The big key there is remembering that the additional mass is the sulfur that we added to the compound. Okay, so that final product has the iron that we started with and the sulfur that we added. So the difference between the two is the sulfur that we added. So that's what we need to remember there, is how we get that mass that was added. Okay? Questions about that one? So we've dealt with empirical formulas. How do I find an empirical formula? How do I take data and go to from that data to getting an empirical formula? That's that lowest whole number ratio of atoms in a molecule. But I don't always want to know what that empirical formula is. Sometimes I need to know what that molecular formula is, exactly how many of what are in it. But I can't always do that from base principles. And if I burn this thing to figure out what components are in it, it doesn't necessarily tell me how many of them there are. I just know the relationship between them. So we won't necessarily know if it's a multiple of that empirical formula. So in order to figure that out, we may have to figure out what's the mass of that material. So there are ways that we can use chemical means to find the molecular weight of something. We can put it in a mass spectrometer and figure out what the overall mass is for that component. So if I know the mass and I know the empirical formula, then I can figure out if it's a multiple. So let's talk about how we do that. So in order to determine a molecular formula, we need to know the approximate molar mass of the compound in addition to finding the empirical formula. So 30.46% nitrogen and 69.54% oxygen. Molar mass is determined to be between 90 and 95 grams per mole. If we do like we've always done, we assume 100 grams of substance, then 30.46 grams of nitrogen and 69.54 grams of oxygen exist. We convert that to moles by dividing by the molecular weight for nitrogen and for oxygen. And we end up with 2.17 moles of nitrogen and 4.346 moles of oxygen. We then put those numbers down here, N 2.174, oxygen 4.346, divide by the smaller number, the 2.174, and that gives me NO2. Now the mass of the NO2, so nitrogen 14.01 plus 2 times that 16, because we're using 16 instead of 15.999, gives me 46.01. And 46.01 is not somewhere between 90 and 95. So I know that that empirical formula is not the correct formula for the thing that I'm looking at, okay? But I can take and multiply that formula by 2 to get N2O4. And if I do that, that molar mass goes from 46.01 to 92.02, which is then consistent. It's between 90 and 95, and therefore my molecular formula is 92. It's N2O4, and the molecular weight is 92.02. Okay? Does that make sense? We knew it wasn't correct because the mass was too small. Therefore, we had to multiply to find one that was within the correct range. Okay? So same process, we then just have to manipulate it a tiny bit more to get to our right answer. You have a compound that's 75.46% carbon, 4.43% hydrogen, and 20.10% oxygen. Molecular weight is 318.31 grams per mole. What's the molecular formula? We again make an assumption that we have 75.46 grams of carbon, 4.43 grams of hydrogen, and 20.10 grams of oxygen, and convert that to moles. We end up with 6.289 moles of carbon, 4.39 moles of hydrogen, and 1.256 moles of oxygen. We divide everything by that 1.256, and we end up with 5.007 moles of carbon, 3.50 moles of hydrogen, and 1 mole of oxygen. But that's not a good ratio, is it? That 3.5 is not a whole number. And I can multiply everything by 2. And then I find that I have C10H7O2. That's a whole number ratio. So this is one of those cases where I have to multiply everything by 2 to get a whole number ratio. The mass of the C10H7O2 is a 10 times 12 plus 7 times 1.008 plus 2 times 16, which gives us 159.06. That's not consistent with the 318.31 that I got. So I can divide the 318.31 by the 159.06, and that gives me a ratio of 2. So I would need to multiply my formula by 2. So C20H14O4 would be the correct formula. So if I have an exact number, I should be able to do that. Questions, comments, problems on how I got there. And there are 2 things that you may have questions about. One is multiplying that formula by 2 in the beginning to get the whole numbers. And then 2, multiplying it again by 2 to make sure that we got the correct molecular weight. Okay. Well, that is everything that I've got in terms of slides. So I want you to go off and practice with some of the materials that we have, D12 practice and the ALEKS practice. If you have questions, comments, problems, please let me know. I will get this loaded as soon as I can, and I hope you guys have a fabulous day. And remember, there is no class on Monday, so I will see you again on Wednesday. Thanks, guys.